Hello everyone. In this session, we're going to delve into the OLS regression analysis and its relevance for time series data. But first, I'd like to take a moment to thoroughly discuss and explain how the ordinary least squares method is effectively performed by walking through a clear numerical example. This is the OLS regression model. We are regressing the dependent variable y, which is the variable we're trying to explain based on the movements of independent variable x. At the conclusion of our analysis, it becomes critically important for us to precisely estimate the values of the key coefficients, specifically the constant term and the beta 1 parameter. For example, consider if we have observed over a period of time specific values of x such as 1, 2, 3, 4, and 5, along with the corresponding values for y. In such a case, we can effectively organize all of these data points into a structured matrix. The first one is a column matrix, specifically for the y variable. The other one, however, has two distinct columns. The first of these is simply the number 1 in every single row, and that will be directly related to the intercept part. The second column in this dataset is specifically related to the x variable. After we have successfully obtained both the y matrix and the x matrix, we then proceed to utilize this specific equation in order to determine the beta coefficients. Therefore, the initial and most crucial step in this process requires us to perform a multiplication of the x matrix by itself. So our initial step involves performing the transpose operation, which essentially means we're converting the data from columns into rows. This is the definition of transpose, and then you must multiply the resulting transpose matrix by the original matrix itself. And when you perform that operation, it essentially means that we are simply taking each individual row and then multiplying it by each corresponding column. If we consider this particular instance just one time, it will contribute a single unit to our overall sum, which then represents the total number of observations. The total number of observations we have is precisely 5. So we are working with 5 distinct observations. That would be the very first element of this matrix here. Then we multiply this row by this column, which simply gives us the sum of the x variable. That's this part. We'll repeat this exact process once more, taking the second row, and then we'll multiply it by the first column, which will then produce for us the exact same element as we had previously, that is, the total sum of all the x values. And we then multiply this by the second column, which will provide us with the value of x squared, summed up over the entire duration of time. This means we are taking each individual x value, squaring it, and then we are adding all of those together. These are the matrix elements, which specifically correspond to this particular section of the calculation. The second crucial step in this process is to calculate the inverse. And the successful computation of that inverse is entirely dependent upon first accurately determining the determinant. And if we apply a specific structure, then that particular arrangement will then provide us with this final matrix. The fundamental idea behind taking the inverse is to have the reciprocal of the elements and to specifically ensure that we completely remove and disentangle any shared directional influence or common trend that might exist between the intercept term and the independent x variable. It's important to recall that in this specific arrangement, we initially have the values 1, 1, and 1, and subsequently we encounter x1, x2, x3, and so on. Now, it's clear that there's a common directional alignment between these two elements, primarily because the x component in some manner consistently moves in conjunction with the y direction. This particular common direction will be removed if we calculate the inverse. Just to make the explanation a little bit easier to understand, let's imagine that we are going to center the variable of x. This means that we will calculate the difference between the individual x value and its corresponding mean value. And we specifically designate this as the centered x variable. If we consider the centered version of our x variable, this would then provide us with the deviation. For instance, the deviation for this particular x value is found to be -2 from the mean, which itself happens to be 3. It's out of d, good size. The deviation of this value from the mean is equal to -1. The deviation of this value from the mean is equal to 0. The deviation of this specific data point from the mean is 1, and the deviation of this other data point is 2. Therefore, we transform our original variable x into a new standard variable x, which precisely represents its deviation from the mean.
And if we take this specific quantity as our primary x variable, then the entire principle of inversion will undoubtedly become perfectly clear.
So if we were to utilize the variable x in this context and then perform the mathematical operation of multiplication followed by calculating its inverse, the result obtained would then be equivalent to 1 divided by t. That value would actually be 0 because the total sum of all the centered x values, if you were to add them up right here, it would then be 0. The negative values will perfectly cancel out the positive ones, and that will be 0.
So 0 element here.
Considering this specific component, the mathematical operation involved would then provide us with a reciprocal value subsequent to our calculation of the inverse of the total sum.
of the square difference between each x value and its central tendency.
The concept of centered x squared is crucial. Therefore, once we have fully grasped this particular aspect, the entire situation will undoubtedly become significantly clearer. The reason we consider multiplying that particular value by this specific term is quite important, as this term itself is directly derived from the preceding process we just discussed. If we take the value of x and then multiply it by y, we are essentially obtaining the y component. The first element, or what we're looking at, will be the sum of y. The second element, on the other hand, is the sum of the product of x and y over time. So if you were to multiply this specific matrix, what we'll do, the first step involves taking this particular matrix and multiplying it by this other specified matrix. Following that, we then take the outcome of that operation and multiply it by this final component. And that would essentially represent the total sum of all white values then divided by the time period t. This means that we are calculating the average value of y, which represents the intercept term. That particular result will indeed be b0. Subsequently, if you were to take the second row and then multiply it once more by this particular value, the product of 0 and this specific element will ultimately be 0. This particular element, when multiplied by this other specific component, will ultimately become a complex expression. It represents the sum of x plus the product of x and y, all divided by the total sum of x squared. Please remember that we're using a centered x as a straightforward example specifically to illustrate the process of how ordinary least squares computes the b0 and b1 coefficients. The centered x, which is x minus the mean, represents the individual deviation of that specific data point. We then square these deviations. This squaring process is fundamental to calculating the variance, which measures the overall variability or spread of all values from their mean. So what we're essentially doing here is taking the product of x and y, which is quite similar to what we call the covariance. We then proceed to divide this value by the variance. This calculation ultimately brings us to the coefficient beta. We are looking at how changes in the variable x can significantly affect the overall relationship that exists between x and y. This, in essence, is precisely the way the coefficient beta is accurately calculated. And the relationship between x and y can be determined through this specific equation, and the beta coefficient, specifically beta 1, will provide us with the precise value. So, the core concept behind using matrix multiplication to determine the beta coefficient, be it beta 0 or beta 1. Now, we have the capability to apply this specific OLS models directly through our dedicated online platform, which is the Finance Research Gate website. However, there are two extremely important considerations we must always keep in mind. The ordinary least squares method will determine the values for coefficients, specifically beta 0 and beta 1, ensuring no statistical relationship between the independent variable x and the residual error term.
So the covariance between x and y is calculated as...
And the error term is precisely equal to 0. There is absolutely no correlation, or indeed there is no linear relationship between the error term and x. This particular requirement is known as the exogeneity condition, and the ordinary least squares method will guarantee that we can accurately determine a coefficient. We are considering the situation where this particular condition is satisfied, and it implies that the numerical value of x is completely unrelated to the error term. Because if these are related, we then have endogeneity, where the coefficient for x is biased, meaning that the beta value we obtain in this case is biased. It's not correct because it's contaminated by the error term. The OLS method will estimate these coefficients in such a way that the independent variable x is not correlated with the random error term. The other thing that we would ideally want to possess and ensure we have in order to truly achieve the best estimator, which is the blue, is this implies that there is no connection or relationship between the current error term and any of its preceding values, which essentially means that we observe no autocorrelation within the error term itself. It is quite possible that could happen with the OLS. So let's consider a specific scenario where we encounter significant autocorrelation within the error component, meaning that this error term demonstrates a clear and measurable dependence on its own preceding values as time progresses. If this specific value happens to not be equal to 0, it clearly indicates that we do not possess a truly accurate estimation for the variance associated with the coefficient that we are examining. Even under these specific conditions, the statistical estimation process remains completely unbiased when applied to the calculated coefficients. So, regarding the expected value for these specific coefficients, it's clear that they are entirely correct, and importantly, they are completely unbiased. The results on average will be equivalent to the actual true value, which clearly indicates that there is no systematic bias present within our estimation process. However, the variance, and therefore the error in the estimation of these particular coefficients, will undoubtedly be significantly biased. So, if that fundamental condition is not properly maintained, which means that there's a significant level of autocorrelation present within the error term, and this specific autocorrelation value is definitively not equal to 0, then the resultant variance calculation When we are attempting to estimate the coefficient beta, whether it's beta 0 or beta 1, the resulting calculation will not be correct or it will be biased. So, after we have successfully fitted the time series ordinary least squares regression model, it is crucial to determine if the residuals, which are the results from this specific regression, exhibit any signs of autocorrelation or not. If these values are not autocorrelated, it implies that the variance and consequently the t-statistics that have been estimated are indeed accurate, and therefore we do not need to undertake any additional adjustments whatsoever. So this is specifically for the regression model, and it's crucial that we pay close attention to the characteristics or diagnostic properties of the error term. Let's now proceed to apply these important analytical concepts directly within the interface of our dedicated website. You'll need to carefully choose the appropriate time series data, specifically opting for a monthly aggregation. Once that's done, we can then proceed to visualize this information by applying it directly onto our interactive charts.
And then at that point, we need to carefully select the appropriate stock return.
That's going to be our y variable.
So, for our example today, we will be performing a regression analysis on the monthly financial returns of a specific company. Let's choose Microsoft for this demonstration. I'll just take a moment to search for that now. We will first click the Enter key, and then we proceed to click the mouse cursor outside of the designated input box. This action ensures that we effectively restrict the display stock tickers exclusively to the specific company we have just searched for.
After you have successfully identified the specific firm you are looking for, you will then need to click on the Apply button.
And then moving into our next phase, specifically in Series B, we will proceed to clearly define the crucial variable X.
This will be a measure of its sensitivity to the overall market, known as beta.
Broadly speaking, the inherent systematic risk is capable of explaining the future rate of return for a particular firm. Our intention is to thoroughly test this specific hypothesis.
So to start, we first need to define the X variable. Then we'll have to carefully select
Our sample firm, which in this particular case is just a single firm.
We're not conducting a cross-sectional or panel regression here because we're exclusively focused on data from just one single firm. Consequently, in this particular scenario, we are performing a time series regression analysis.
We're selecting the Microsoft option here. And then we go ahead and apply it.
Following that initial step, it becomes necessary for us to thoroughly check for the stationarity of both of the involved variables. From our careful observation, the monthly return data clearly shows stationarity, as is clearly indicated by the augmented Dickey-Fuller test shows a certain outcome, but this is not the situation for the beta coefficient, which means the underlying relationship is not truly stable. The distribution of market beta is fundamentally determined by its position in time. Its inherent temporal dependency could potentially result in a spurious relationship if we were to incorporate that specific variable into our regression model. So we need to transform the non-stationary variable, the market beta, into a stationary one. The most effective approach, or perhaps the standard method, involves utilizing the first difference. So I'm going to navigate to the Derive New Series box.
Then I choose the beta, then I name the new variable as differenced beta.
I've decided to go with the time series transform, considering the entire family of methods, and then moving forward from that point, the way the transform function is currently presented right now is the crucial and significant difference. These should allow a sufficient amount of time to pass, and subsequently, we will identify the key differences, and finally, we can proceed to construct the entire series.
Following the successful generation of our complete data series, it's important that we implement a specific lagging operation. This will result in a single distinct interval being placed between the corresponding y and x elements.
So our preference is to have just one single gap in the overall schedule, and that gap specifically would be a 1-month period occurring between y and x.
So, in this particular scenario, we utilize the dedicated lag creation function, carefully select the difference beta parameter, and then we proceed to generate just a single lag, which we subsequently add.
Once we have successfully recreated the necessary lagged variable, we will then be ready to begin the regression analysis.
In order to start the regression, our goal is to accurately identify and then select the optimal regression-based time series model for this analysis. So in this particular analysis, we are examining the full set of endogenous variables. The primary exogenous regressor, which is independent of our system, is specifically the lagged difference in beta values. And then our key dependent variable, which we denote as y, is defined as...
Looking at the monthly return, you can see the y-axis here and then the x-axis over there. We need to make sure to say the residuals that are generated from our regression model. This particular output, which represents the error terms, can be stored and subsequently estimated once the regression process has been fully executed. Because once we've run the regression, we can then estimate the coefficient, pause, and subsequently the error can be determined by comparing it to the actual observed value, subtracting the estimated value that this specific model provides. The estimated value is simply calculated by taking the constant term, then adding the slope, also known as beta 1, which is multiplied by the independent variable, our x value. Therefore, if we take the predicted value and subtract it from the actual result, that calculation will provide us with the estimated error. We need to check for any autocorrelation in the error term. If such a situation arises, it means that the calculated variance and the estimation of the coefficient are incorrect, which then invalidates the t-statistics. The information provided concerning the beta version is entirely incorrect.
So, once that particular phase is successfully completed, we then proceed to meticulously assign a descriptive name to all of the previously saved residual data points. And following that, we carefully fit the regression model. Let's take a moment to consider this next point. Here we have the coefficient estimation.
Regarding the beta, it's not statistically significant, indicating that there might be additional factors influencing the monthly return for our specific firm. The constant term in our statistical model is found to be statistically significant at the 1% significance level, and its calculated value is exactly 1.08%. So, when we consider the average monthly return, we find that Microsoft's consistent monthly return is precisely 1.08%, and that in itself is quite significant. For the coefficient we chose here, it's negative, but not significant. Now, the important question we need to address is, how do we determine if this specific coefficient is statistically significant?
In statistical analysis, we often focus on either the t-value or the p-value. The t-value is simply a calculated statistic.
The t-value is the estimate or the estimated coefficient, in this case, beta 1, divided by the standard error. Write this down in a clear way. Manner.
Standard error.
This value, which is derived directly from this calculation, will then represent our estimated standard error. This crucial component will then be employed in the process of determining the t-statistics.
Thus far, our assessment has led us to conclude that it is not statistically significant. However, if there happens to be any form of error autocorrelation present, then our ultimate conclusion concerning the t-value will in fact be incorrect. So, let's now carefully examine if we detect any significant error autocorrelation. We should specifically analyze the residuals to ascertain the presence of any such patterns. The most straightforward and effective method is to simply scroll down to the very end of the output
And then we should take a look at the ACF chart for the error. So it's important that we make sure to change that. We then proceed to save the residuals so that we can effectively utilize that within the series here, specifically inside the ACF, which is the autocorrelation diagnostic box. Once we select the save the residuals, we then check for any autocorrelation.
Now, if we carefully observe the results presented here, we can clearly see that at lag 1, lag 2, or any other lag, we don't have any evidence of significant autocorrelation. What this essentially indicates is that a significant correlation does not exist between the variable AT or alternatively AT minus K, where K in this context denotes the time lag. We could be looking at a lag of 1, or possibly a lag of 2, or even a lag of 3, and so on. In this specific instance, when we examine the various lags from lag 1 up to lag 40, we can confidently state there is no discernible error autocorrelation present.
What this essentially means is that the error is not correlated with its own previous values,
And that will make the estimation of the t-statistic accurate, and the conclusion of having non-significance for the chosen x is also correct.
It's important for us to thoroughly examine and understand the significance of the remaining co-coefficients that have been clearly presented and laid out for us within the comprehensive data table.
Or other statistics, we also have a joint test, a test for the normality of the residuals, and the omnibus test. Here, the interpretation is that the p-value is essentially 0. Therefore, we reject the hypothesis of normality. The error distribution itself is clearly not normal. The Jarque-Bera test also provides strong evidence and concludes that we must reject the assumption of normality for the model's residuals.
Upon examination, we observe significant skewness, specifically a left skew, and also a noticeable presence of kurtosis. This clearly indicates that our error distribution is not normal. Please remember that the error term is essentially the unexplained movement or variation in the y variable, even after we have carefully fitted the x variable.
So after we have fully accounted for the initial x variable in our analysis, and then also factored in the suggested x, which was specifically defined as the change in beta, any remaining portion that cannot be adequately explained by these two elements, the portion of the data not explained by the constant nor by the variable x, the particular error term exhibited non-normality characteristics as clearly indicated by these statistical tests.
The Durbin-Watson test also checks for autocorrelation, but only for first-order autocorrelation.
And here, we arrive at the very same conclusion, primarily because the Durbin-Watson test is clearly indicating a value that is quite close to the number 2. So, if I were to go back now,
We'll start by performing the Durbin test, and then I'll quickly run the statistical regression. It's incredibly close to reaching the 2-point threshold, almost exactly there. The precise reading, if you look closely at the display, is actually 2.16. When the Durbin-Watson statistic is close to a value of 2, it indicates that we do not have any significant first-order correlation. However, if its value is close to 0, this suggests that we have a strong positive core autocorrelation. If the value is close to 4, it indicates a very strong negative autocorrelation. In our specific case, we do not have any error autocorrelation.
it's not just limited to the first order, as we previously confirmed and saw, the ACF chart clearly shows no autocorrelation whatsoever.
But what if we had an
Error autocorrelation. How can we go about correcting for that?
One effective approach involves utilizing the GLS, which stands for Generalized Least Squares. If in this scenario we encounter an error autocorrelation, it implies that the autocorrelation itself will exhibit a form of memory,
Meaning that it is a direct function of the previous error.
The raw coefficient that we're considering here, which is typically going to be a value that is almost always lower than 1, will clearly indicate to you the magnitude of the autocorrelation effect.
For example, if it is 0.5, it means that it will carry 0.5 of the previous period's errors.
In order to effectively remove this issue, according to the generalized least squares method, we are required to transform both the y variable and the x variable. In simple terms, we subtract the variable y from the product of our HO and the previous calculated value. It is this previous value that inherently contains the error.
1 second until launch. So by subtracting that previous error term, which is autocorrelated with YT, we are effectively removing a source of BS, meaning that we achieve a much cleaner and more reliable estimate. The Y variable in the process of removing the autocorrelation of the error from the immediately preceding observation. Similarly, we perform a subtraction operation where we take the previous X value, multiply it by the error autocorrelation coefficient, and then remove that product from the current observed value. Through this particular approach, we are systematically eliminating the detrimental effect of the error autocorrelation from both the Y and X variables. Once we have successfully obtained these new Y and X values, we then proceed to run the standard ordinary least squares regression. The standard OLS approach in this specific situation should be entirely free from any error autocorrelation because we have simply removed it and consequently we are left with only white noise. So in this particular scenario, we have the option to proceed with our analysis by employing the generalized least squares method. Therefore, it becomes necessary for us to transition and implement GLS for this task. Additionally, I will also need to ensure that the residuals are appropriately adjusted to reflect the GLS methodology.
Now we're presented with two distinct choices, the Praise-Win, Winston, or the Cochrane-Orcutt approach.
The distinction between these two methods isn't particularly large. With regard to the first method, the one we call the Cochrane-Orcutt approach, our process involves using the data once it has been transformed. However, when we execute this particular process that I previously described, we are expected to lose a single observation. So what exactly would be the corresponding YT value for that initial observation?
We require an observation at the time point 0, but that cannot truly exist since we're deducting a part of the past value.
So, for the first observation within our data sample, we don't possess a previous value to reference. Therefore, we must omit the very first observation so that we can proceed with the required data transformation. So, this transformation will commence at the second period, specifically at the second period for both the Y and the X coordinates. So, with the Cochrane-Orcutt approach, what this means is that it's perfectly fine to sacrifice the very first observation. Then we will have T-1 data points remaining for our OLS regression. What we do quite simply is we just drop the very first observation point. We're going to keep the Praise-Winston approach, but we'll be employing a modified first RHO transformation. We create out a particular RHO transformation. This is done by utilizing the AR1 model, which specifically accounts for the autocorrelation structure to effectively establish the very first observation point.
For this situation, we can simply use the Cochrane approach since we possess a long sample.
So we have 24 years, and each of those years has 12 months. We have large samples, so we can certainly afford to lose just one observation. That's something that is absolutely normal.
And once we have selected the GLS transformation,
Then we can proceed to accurately fit the statistical regression analysis.
now here, the T value
Things have been significantly altered, and it's quite evident that the T value, as well as the standard error, has undergone a noticeable recent adjustment because of that particular fix.
Allow me to proceed and execute the OLS regression analysis. I want to clearly observe and understand the specific nature of that particular change. We'll focus on this section, for instance, this specific part of the data.
and the change will definitely happen.
See, if you look closely, you'll notice that the numerical values on the screen have just changed. Specifically, both the crucial T value and the associated standard error have been updated.
So, GLS represents another method to address the error autocorrelation.
In our specific situation, we don't need to do that because the initial error term did not show any significant autocorrelation. If you prefer to use the generalized least squares method, that would also be perfectly acceptable.
All right, that's everything for today. Thank you for listening.